AVL tree, where AVL tree is a balanced binary search tree. It is an efficient way to search an element in the AVL tree. Why we call it as AVL tree, we know, we have seen, and we have seen the balanced factor also. What is balanced factor of AVL tree? And today we are going to see the B tree. It is also a kind of tree where it can have multiple children's. So that's what we are told, like this B tree is a specialized multi-way tree that can be widely used for disk access. So what is the application of B tree? So we have seen each and every tree and also its application. So the reasoning of tree is for some application only. So what is the use of this B tree? For the secondary storage access. You know, secondary storage like ROM. Okay, to access a large storage if the capacity is more. So we have going to access particular data from the disk. For this purpose we are using B tree. And you know why we are using, or we have seen the data structures. We have seen several types of data structures: linked list, then queue, stack, trees. Okay, so data structure is that where we are efficiently organizing the data so that it can be accessed easily or quickly from the memory. Okay, so the B tree is a multi-way, or we say is a M-way tree that can be widely used for disk access. So a B tree of order M can have at most M minus 1 keys and M children. So here I will tell about the order M. So here I will tell about what is order M. Okay, so if it is order M for a particular node, if it is order M, it has M children. Okay, if the order is 3, okay, if the order is 3, a node can have up to 3 children, for example. Then what about the keys? It can have M minus 1 key. If it is 3-way tree, so here I told multi-way tree. If it is like multi instance, here I'm using 3-way. The order is M. Okay, I call it as 3-way tree. So in the 3-way tree, what are the how many keys I can have? 2 keys and have M minus 1. So that is a formula we are using, mathematical calculation we are using to have how many keys in a particular node. So you know what is key. In case of binary search, we call the key as the element. Okay, so key is some element, some notation where from that we are going to track the elements. Whether I want to, with this key, I want to track towards the left subtree, or I have to track towards the right subtree. So that's what we are telling is the key. Okay, and so far we have seen the key as the element. We have seen the key as the element. Okay, now we will come. So order M. Okay, for example, B tree of order M, B tree of order 3 can have 2 keys and 3 children. So what is the advantage of this B tree? It is capable to store large number of keys in a single node. To store large values, key values, by keeping the height of the tree relatively small. Okay, so what is the main reason for this? Instead of having n number of heights, n number of edges in the tree, we will keep the tree height as small as possible, so that all the elements in the tree will be accommodated at the minimum levels. Instead of having the 5, or for example 10 keys in 10 elements in 5 levels, I can have the 10 elements in the 3 levels itself. It is possible. So the advantage of this B tree is that I will make the all the elements in the key with the smallest height, so that it then search operation is very easy for me. Okay, the third one is will be used when the data to be accessed, stored, is located in the secondary storage devices. So it is meant designed for the secondary storage. You know, the secondary storage is a large amount of memory. For this purpose we are going for B tree. So before getting into B tree, we'll say about M-way tree, that is called multi-way tree. So multi-way search tree is Okay, for example, I can say that even the binary tree also I can say is a multi-way tree. Why? Because the binary tree can have up to two children. Okay, I can say that two-way tree. Binary tree is the two-way tree, right? Because it is having two children, and for these two children, and m minus 1 is what? 1. So it has only one key, right? So the root node consists of one key and have two children. So that's what we are saying. The multi-way tree, multi-way search tree is a generalization of the binary search tree. Again, we can track backwards also, vice versa. Okay, I can say this binary search tree as a multi-way tree. I can call the multi-way tree as the binary search tree. I can call both ways. By definition, actually, what is m-way tree? Each node has m children and m minus 1 key fields. The keys in each node are in ascending order. Okay, this we have seen. Okay, this given very clear picture. And the second is the keys in each node are in ascending order. When you are inserting the element into the tree, for example, in m-way tree or binary search tree, whatever the case, okay, while inserting itself, you will make the elements in ascending order, so that while searching an element, for insertion it takes some time. While insertion takes some time, but in case of searching, it is very easy for me. Why? Because it is already in sorted order. So the keys in each and every node will be in sorted order. For example, four-way tree. I'm telling about four-way tree. Okay, four-way tree consists of what? 4 children. Okay, and each children can have up to 3 keys. Okay, each children can have up to 3 keys. That's what m minus 1 I told. 4 minus 1, 3 keys. So all the 3 keys will be in sorted order. Okay, that is the advantage of the m-way tree. So more than one key is multi-way search tree. Okay, example. This is example shown. So this is 3 children. Okay, this is a 3 children and 2 key. So I call this tree as a 3-way search tree. This tree as a 3-way search tree. Okay, why? Because for a node I am having 3 children. Okay, this node I can call this not this as a binary tree. Okay, because binary tree will have only 2 nodes, that you know. And in case of, look at the keys, you have 2 keys. I shown the edges like this. The first key, okay, the elements which are lesser than the first key is the children, is the first children. The lesser than 20 all comes under the first children. Okay, if it is, I'm inserting 17, for example, next nodes comes, next element comes, 17 I'm going to insert in this tree. What happens? 17 comes here. 17 comes here. Okay, for example, I'm inserting 21 for inserting 21. So you know that this 21 is between 20 and 50. So automatically we are writing an algorithm where should the element should be inserted, where the element should be inserted. When a 21 comes, what I'll do, I'll directly insert in the second children. Okay, I cannot write this 21 here. Okay, it is inserted here, but it is wrong. Why? Because it automatically inserts in this position 21. We told it will be in ascending order. While insertion, it does all the things. It will be in ascending order. So for a three-way search tree, a node has 3 children. 1, 2, 3. 1, 2, 3 children. And it has 2 keys. Here key is representing the some decision here, which side the element should be placed, in which children the element should be placed. Okay, and same way, so m ways has m minus 1 keys and m children. Okay, fine. B tree of order m. Okay, so B tree of order m. So now I'm telling what is actually B tree. So order can be m. So here I'm saying the order. You can say is degree or order. You can say degree m or order m. So every node has at most m children, and every non-leaf node except the root has at least m by 2 child nodes. So what is this? This operator, you know, this is a what? This is a seal operator, sealing operator. Okay, at most at least m by 2 nodes. For example, is 10 order 10. For example, order 10. I'm taking example B tree of order 10. So what I say, m is now 10. So 10 by 2, 10 by 2 is 5. Okay, simply it is 5. If it is like, for example, you take 9, I am taking order 9. Okay, B tree of order 9. So 9 by 2, 9 by 2 is what? 4.5. So 4.5, the seal operator, when I apply seal operator for 4.5, it becomes 5. Okay, so that's what here it's mentioning. So for 9 order 9 or degree 9 tree, I can have at least what? I can have at least 5 children's, 5 child nodes. Okay, that is the meaning for this. Okay, you have to represent, while explaining this B tree, you have to mention this seal operator. That is important. How many child nodes can be for a non-leaf node except the root node? Here the non-leaf node is representing except the root node. Okay, internal nodes. Okay, internal nodes, it's representing indirectly, it's representing the internal nodes. The internal nodes can have up to, sorry, at least m by 2 children's. Okay, the root has at least 2 children if it is not a leaf node. Okay, if it is not leaf node, at least it can have 2 children. So keep in mind, the root will have 2 children. A non-leaf node with k children contains k minus 1 keys. Okay, obviously we have discussed the same thing. Okay, it has k minus 1 key. All leaves appear in the same level. This is the important property of the B tree. So what I mentioned in the slide is the properties of the B tree. We know that we have seen the properties of each and every tree. What is binary tree? What is binary search tree? What is the property of AVL tree? Like that, when I ask for B tree property or the structure of how the structure of the B tree looks like, then you have to tell all these things. Okay, here the leaves will be at the same level. Okay, that is important here. And one more thing, you can add the point here, and all the elements in the node will be in ascending order. Okay, and the other point is that the tree is built from the bottom up. That I will show in the next diagram, how the tree is built. Okay, the tree is built from the bottom up. When you take binary tree, for example, binary tree, it will be built from the top down. Okay, whenever I insert an element, okay, it is built from top down. Okay, whereas in case of B tree, it is built from the bottom up. Okay, next. B tree. So 4 node consists of what? 3 keys, 4 minus 1, 3 keys and 4 children at most. So here these are all keys, 10, 30, 34, all are keys, and the elements will be placed based upon the keys. Okay, this is a example of 4 node key. So I'm going to take how we are going to insert in the 4 node key. Okay, this is the current stage. This is the current stage. Now I am going to insert. So these are the elements in the tree. So we told that in a particular node, we can have at most of 3 children only. Okay, right now what happens, all the nodes is having 1, 2 or 3 children. Okay, fine. The root node is having 2 children. Now I'm going to insert 2 comma 2, 2 comma t, nothing but I'm going to insert 2 in the tree. We know that whenever I insert a 2, it automatically comes to this position. Okay, so it's expressed 14, it comes from the root node, it directly comes to this position, to this node, and again it checks for the keys. Okay, it is lesser than 5. If it is lesser than 5, it goes to the first children. So in this position, in this child node, the element 2 is inserted. See, then next is made it as green. Okay, so here we are shown the node with 3 children is with green color. Okay, a node with 2 children is highlighted with red color, and single with blue color. So now I inserted 2. Fine, there's no problem at all. If I'm trying to insert, for example, 4, There comes the problem. Okay, we told that it should have at most of 3 children only. It should not have more than what 4 keys in an element. Okay, if I try to insert an element 4, it automatically will come here only. When I try to insert an element 4, it automatically comes here. Okay, based on the rule. But this is not the property of the B tree. Okay, so it can have at most of only 3 keys. Though the element itself is acting as a key. Here, all the elements is acting as a key. Okay, we'll see next thing. Okay. Next 4, you are inserting the element 4. What happens? So it comes to this position. Okay, right now it is in this position. We have to split the node. We have to split the node. 1, 2, 3, 4, right? So it automatically comes to this position. We know that it should be in ascending order. When I insert 4, it's automatically is sorted. Okay, when exceeds the limit, what happens? This node should be splitted into 2 nodes, 3, 4. Okay, so this is one node. This is one node. It's not 12. It is 1, 2. Okay, and this is another node, 3, 4. Okay. Next, what should I do? I have to push the one element either from the root node, either from this left node or right node to the ancestor node. Next, I'll show it. See what happens. It was, I splitted 1, 2. Okay, 3, 4 it is there. Next, what happens? Automatically, the 3 is what? Taken as the key. The 3 is taken as the key. Okay, and placed in the root of these 2 child nodes. So what this means here? When I take this 3, we know why I am splitting the key, why I am making here 3 here, because whenever the element comes lesser than 3, it will be placed in the towards the first child. Okay, and here the second child represents what it actually represents, that 3 and the elements greater than 3, that is greater than 3 and lesser than 5. It means that 3 and 5 between the elements between 3 and 5 will be placed in the second children. So the fourth element comes, means, see, keep in mind we are taking the 4 order. Okay, we are taking 4 order. If it is 5 order, what you have to do, each element can have 4 keys. Okay, in our case it is 4 order, so it can have what? Each node can have 4 children and 3 keys only. That if it exceeds, the 3 keys exceeds, what I have to do, I have to split the node. That is the condition here. That's all. So I split it. I made this 3 here. If any elements comes between 3 and 5, it represented 3 and above will be placed in the second node. 5 and above will be placed in the third node. 9 and above will be placed in the last node of this. The last child of this node. Okay, fine. Next, I am inserting 6. So where the 6 will automatically goes. So 6, 5, it will be between 5 and 9. So here it comes. No problem. Okay, it directly comes to this third child of this node. Okay, keep in mind these are all keys here. 3 is a key, 5 is a key, 9 is a key. Okay, so green color, yellow color is highlighted where the 6th element is inserted. Okay, fine. Next 7 comes. What happened? So we know that 5 and 9, between 5 and 9, it automatically comes to this position. Okay, no issues. Okay, once it becomes 3 keys, it has been highlighted with the green color. So 7 comes to this position, no issue. Then 8. What happens? 8. If 8 comes here, so according to the property, it is not satisfying. So we have to split this. We have to split the node, 5, 6 in one node and 7, 8 in one node. Okay, then what I will do, I have to make this 5. After 5, I can have 7. Okay, that I will show you clearly. So 8 is inserted. Okay, after 8 is inserted, what happens? So I splitted 5 6 7 8. Okay, I have splitted. Right now I have splitted only. I didn't add any element to the ancestor. Still I didn't add any element. Some element should be placed over here in the what? Some no element should be placed in the this node. What happens? So I told 7 will come here. 7 and above. Okay, 7 and above will be placed in the fourth child. Okay, 9 and above will be placed in the last child. And we have seen here how many childs. After splitting, what happens? It automatically becomes what? 1 2 3 4 5. It becomes what? 5 children. It should not happen. It should not happen. See, it is violating the rule. It should have what? At most 4 children only. But now it is 5 children. Okay, what should I do? I will split this now. I will, because it is also exceeds the key value, number of keys. 3 becomes 4 now. It's also violated. So I will split this. Okay, I will split this. So 3 5 is splitted. Okay, 3 5 7 9. It was actually, it was a prayer. It was like that. Then I divided the node 3 5 7 9. Okay, when I do like this, what happens? It automatically 7 and above will come here. Okay, what about this? This will come here, right? It can be inserted this side or that side. Okay, so what is the logic here? What is the logic here? So 3 5, and we told after splitting a node, what should you do? What should I do? I should move the element from the node, right? From the 4 elements, I have to move one element to the root. I have to move one element from the node, either from this node 3 5 or 7 9. See, I did like this previously. I did when inserting. I'll show. Go back to the slide. When I'm inserting 4 here, when I'm inserting 4 here, what happens? I splitted. Then automatically when I splitted, automatically 3 goes to the, becomes the key of the ancestor. Okay, like that. When I split this node, particular node, okay, one of the nodes should be moved to the ancestor. Okay, that's what it's happening like this. So when inserting 8, so I divided the nodes. Then any of the element from this node or this node should be moved to the ancestor node. So what happens? The 3 and 5 is there. No, I have moved this 3. I have moved the 5 to the particular node. I can even move the 7 also. I can either move the 7 comma 14, 7 14, 7 comma 14, or 5 comma 14. It means that both are same only. Okay, 5 and 14. The between elements node between 5 and 14 will be placed between the what? If you want to place 7, I will place between 5 and 14 only. Both are same. Either I can put 5 or 7. In this representation, we have placed 5. Okay, we have placed